Welcome back. This is Project 1, Part B, where we're going to focus on processor management. As usual, we do need the lab manual, so you want to review the Chapter 9 and Chapter 10 contents. We've gone through them in the Lab 10 video, where we introduced the system calls, interrupt handlers, and the processor. These concepts are very important for you to understand the context switching part of Part B of Lab 1. And 5.1 section is the requirement of P1, so you want to go through that. And 5.2 is the demonstration procedure, and you also want to go through that in detail. And the 5.3 is the testing framework. You want to take a closer look at it so that you know which files you can modify and which files you cannot modify. And section 1.1 to 1.2 is an overview of the RTOS project. Please review it so that you can have a higher level of understanding of what this project is about and where does P1 fit into this project. And then finally, the most important part is 2.3. That's the processor management API requirements. So you need to basically study it in detail. And then 6.1, that's the FAQ part that is related to the processor management. So in Part B, we continue working on our multi-programming kernel. This just want to remind everyone, we have fixed the number of coexisting processes in the system. And in Part B, like the entire Part 1, right? The B part is the same. We have 7 processes. And Part B, the main job for you is to do the scheduling part. So we're going to do what we call priority-based preemptive no-time slicing scheduler. What does that mean? It basically means each process has a priority. And if I have multiple processes, they are all ready to run, then whoever has the higher priority will start to run first. And if they're all at the same priority, so within the same level of priority, first come, first serve. Preemptive basically means I'm a running process, and then something happens, either a hardware interrupt or a system call, which is a software interrupt, that makes another process become ready, and that the new process has higher priority than the current running process, then the new process will take over the CPU. So that's what preemption is about. No time slicing basically means we don't really have a time quantum. If a process gets the CPU, it will keep running until it gets blocked or by the system, or it voluntarily releases the processor. And then the memory management part. In Part A, we were basically mainly focusing on the non-blocking version of a fixed size memory pool. But now in this Part B, we're going to add more features to it. First, we're going to make our memory allocator a blocking one. So if a process requests a memory and there's no memory, this process will get blocked. So although we say it is under the memory management, and as you can see, this is really processor related behavior. And that's why we do it in Part B. And the other one is we introduce this notion of ownership of a memory block. So whoever requests the memory block, that process owns that memory block. We don't really use hardware to enforce the memory ownership in this project. So we use software to do this limited control. That basically means if I'm P1, process 1, I request a memory, and then say a P2, a process 2, tries to release the same memory block, then the operating system at the software level won't allow this. We've already done P1A, where we have the basic memory allocator, but now we want to add blocking and ownership feature. Then we will be mainly focusing on the priority management, which is set process priority and get process priority. The release processor is almost done for you, but what you need to do is to make sure the release processor will work after you add multiple ready queues, because in the starter code, we don't really have a notion of ready queue. So what's new about the requirements on processes? For now, process we want it to be at a hidden priority level, which is 4. And this is the only process that is allowed to be at this priority level. And for the test processes, we still have 6, but you need to write new testing cases to test anything new you implemented in Part B, for example, the priority management, and also ownership of the memory block and the blocking feature of the memory allocator. And for the initialization, now we're doing priority management. So the data structure to manage the processor or processes, they need to be initialized during the initialization time. So this is just a reminder that all our processes, they never terminate, and we do not create new process on the fly. So how does the RTOS know which processes to create? We're going to predefine an initialization table, which is an array of records, and each record contains the specification of a process. Important information of specification includes process ID, the initial priority, stack information, and the entry point of the process. In the starter code, we have a comment.h file where we have defined a process initialization record data structure. And you can see we have 4 fields, basically the PID, the priority, the stack size of the process, and finally the entry point of the process. The entry point of the process is a function pointer. So in our case, our process, they are written inside a function. So you give the entry point of the function, and that's the entry point of that process. And again, the initialization table is basically just an array of these records. So in the starter code, we have ae_proc.h file. We have declared all the function prototypes of processes. And here are the 2 test processes we implemented in the starter code. And if you look at ae_proc.c file, you will find the first function is set test procs. So you look at the prototype, right? This is a pointer to point to the process initialization record. So this basically is an array. And here the second parameter says how many records are there in this array. And then we just loop through and we assign PID, we assign priority, we assign the stack size, and then finally we assign the entry points. So for your case, you're going to program ae_proc with a number, and this number needs to be from 1 to 99.c. So 1 basically means testing suite 1, 2 testing suite 2, so on. And for us, when we provide you the testing suite file, and for P1 we will use ID 100 to 199 and 200 to 299 for P2 and 300 to 399 for P3. The process initialization table gets passed in as one of the arguments to the RTX init function, and the number of elements inside this table is the second argument. This function, once it finishes, it will execute one of the processes inside this table. Which process is decided by the priority. Whoever has the highest priority will be chosen to run as the first process. This function does not return. You may wonder, what if something goes wrong during the initialization? For example, I may not have enough memory to initialize stuff. Well, of course, technically, we could put it as an int return and then let this function to have a return error. But we just assume this type of situation will not happen in our simplified version of project. So we assume this function always succeeds. In order to support multi-programming kernel, we need to be able to support multiple processes. So what we're really doing is to virtualize the processor. We only have one processor on this particular board, but we want to be able to have the illusion that we have multiple processors. So we're virtualizing the processor. Now the question is, how do we virtualize the processor? A processor is used for execution of instructions. So the question now becomes, how do we represent a stream of execution? So a piece of information we need to represent is the execution state. This includes the machine state, which basically means CPU registers, and the stack. That is very important. ARM requires the stack to be 8 bytes aligned, so I want you to keep that in mind. Another piece of information we need to represent is the management state, especially those that frequently changes. This includes the process state. Is the process in ready state, or blocked state, or some other states. And then management information that changes less often, we also need to record them somewhere. And this includes process ID, the entry point, these two never changes. And priority, well, they change less often. If you want to change it, you have to call the set priority to change the priority. So the data structure to represent the virtualized processor is basically what we call the process control block, the PCB. And we need this for each process. It describes the status and the context of a process. In the starter code, we have predefined some states, let's say the new state, the ready state, the run state, and you need to add more states. For example, in this project, you have to add a blocked memory state. And then the PCB, we give you a very simple one to get you started. So this one, it has a linked list data structure, so it links to the next ready process if you want to put all the PCBs on the ready queue. It has a stack pointer and has a PID and the current priority and the state. And then you want to add your own fields here, so expand this data structure. So here's the P1 process state transition diagram. Just to remind you, you have to add the blocked on memory state because we're going to make the memory allocator a blocking call. It basically means whenever I request some memory and memory is not available, then the process gets put into the blocked on memory state. So assuming this is the process that is already run, and then I request memory, and there's no memory available, so I'm in blocked memory. But then somebody released the memory becomes available, I become ready. And then release processor can basically make a run process go back to ready state. And also, if I'm in a running state and then there's a higher priority process gets scheduled, I also go back to ready state. And you may not see this in the lecture, but it appears in this lab starter code. It's the new state. This can be considered as a special ready state. So I have a process I just created, and we call it new state. And if the scheduler picks it, then instead of going to the ready and then go to run, it directly goes to run state. So this can be considered as a special ready state. Why are we doing this? Purely for programming convenience purpose. It's just like when we start a process that has never been run before, the way we program it is different from where we resuming a process that has already been run once, or at least once. So we've seen this slide, maybe a little bit different from the part A tutorial. But what is new? What is new is this part, the process control kernel data structure, the PCB kernel stacks. This part needs to be added to part B. And create PCBs of all processes. So this part is new because we're doing processor management. And when we do the PCBs, okay, you need to basically include the privilege level information somewhere, most likely in the PCB data structure. And we need to use the privilege level information to program the control register. And I do have an example in the starter code for the new state process. How do we set the control register? So take a look at that. And for the exception stack frame creation for new process, we already done that part for you. And allocating stacks requires playing with the memory. So let's take a look at the memory map. So the starter code put two process stacks on top of the high address of the IRAM1 and put PCBs here. And this is your RTOS image. End of image, we have this symbol, and sometimes you may want to add paddings. That's optional. And you may want to, and we put two PCB pointers here. So now you're going to expand this with more processes, so you're going to have more stacks like going down this way and more PCBs going up that way. So that's basically what you're going to do. So the GP PCBs, this is a global variable, points to the PCB array, and the GP stack points to the stack. So this one basically means going down. These are the free space you can use for new stack. We've already seen this diagram in the first tutorial where we went through the exception handling mechanism. I want to remind you that when you submit your project, we assume this macro is not defined. So in the starter code, what we're giving you actually is this part. We give you two privileged processes, so Proc1 and Proc2, their privilege level. But in the submission requirement, we require these two processes to be at unprivileged level. So that basically means you need to change the process management C file so that you set the control bit at the proper place, so your process will be running at unprivileged level. To create a new process and start to run it requires some special treatment. While we're in the initialization phase, once we're done with everything, we want to start our very first process. Think about a naive way. We just directly call the function that implements the process. What's the problem with this approach? Well, we're in handler mode, and we want this process, when it starts to run, to be at thread mode. So there needs to be a mode switching. So I can't just directly do a function call. So what we need to do is somehow to invoke the exception return mechanism so that when the process starts to run, it will run in thread mode. Here is the routine to do the exception return, and it's called return from exception. And this routine, before it enters, it assumes an exception stack frame is already created on the current stack. So all we need to do is to manually create the exception stack frame for the new process. So inside k_process.c, there's a function called process init. I have put the code that to create the exception stack frame here. So for each single process, we create a exception stack frame manually. So how do we do it? We first allocate some stack space for the process. And once we allocate the stack space, this is where the SP starts. And then we're going to manually write to the memory location to create this exception stack frame. And we have a fully descending stack. Basically means every time we want to push an item, we decrement the stack pointer, then write the item, like put the item into that memory location. So in the C code, we decrement, dereference it, and then we put the value in it. And then that's the XPSR, this program status register. And the second item is the PC, the entry point. So we put the entry point at the PC position. So you can see from the initialization table record, we got the entry point. And then for the rest of the registers, we just put zeros because it doesn't really matter. We never run this process before, so 0 should be fine. And then finally, we set the stack pointer to point to the new location. So once we have all these things set, and then we invoke the RTE __ RTE, which is return from exception, and that is return from exception routine assumes the the SP points to here, then it will pop off all these registers from the exception stack frame. Then what happens to the PC is the entry point gets written to the PC. Then so our first program starts to run, and at the correct mode, we are in thread mode. So we need a global variable. Let's say we call it current process. Well, instead of the starter code, the name may be different, but the purpose is the same. So this variable always points to the current running process's PCB, because at any moment, OS must know who is using the CPU. And we only have a single core in our lab, so that's why a single variable should be fine. But if we have multiple cores, then we need this variable per core. With the PCB data structure, it allows us to perform the process switch. The process switch has two parts. One is the policy part, the other one is the mechanism part. The policy part basically means it needs to make a decision on who will use the CPU next. And then once we know who will be the process that to execute the CPU, then we in this mechanism part, which will do a context switching to switch from the current running process to the new process. And this context switching involves updating the PCB, update ready queue, and finally, the most interesting one is to switch the stacks of the two processes, which effectively will do the context switching. I'm going to start with the discussion of scheduler, and then I will move on to the context switching part. The scheduling requirement I've already went through at the very beginning of the tutorial, so let's just refresh our memory. First, no time slicing. Second, fixed priority-based scheduling. Third, it is preemptive. And then finally, each process has an assigned priority, and the highest priority process should execute first. And within the same priority, we do first come, first serve. And in the comment.h file, you will find all the defined priorities. And this one is a reserved one for now process only. The preemptive part of the scheduler means if I'm running and then for some reason, let's say an interrupt happens, either software interrupt or hardware interrupt happened, it makes another higher priority process ready, then the kernel will run this higher priority process. Then what happens to the current running process? It will be preempted. Then what does it mean in sense of data structure? It basically means inside the PCB, then its state will be changed to ready. And what happens to the ready queue? Then this process, which gets preempted, will remain its position in the ready queue. So it will be at the front of the ready queue because it was running, right? And now it's taken out from the CPU. So it is ahead from all the other processes that are within the same priority in that ready queue. So it should be put at the front of the ready queue if it is preempted. So preemption implies the following situation should never happen. So let's say I have P1 that is ready and P2 is in run state, but P1 has higher priority than P2, then this basically means you definitely have an incorrect scheduler. The scheduling procedure involves three steps. First, the kernel will invoke the scheduler. Then the scheduler will select the highest priority ready process. Then finally, the process switch function gets invoked to switch in the new process. And we already have a process switch function done for you in the starter code that does most of the work. Ready queue is one of the most important data structures for the scheduler. And one implementation for our lab is to have an array of ready queues. So each priority has a ready queue. And for each ready queue, we can use linked list to implement this queue. So now let's talk more about this now process. As I mentioned in the previous tutorial, the CPU must execute something at any moment. So what if we don't have any processes ready to run? That would be a problem. This could happen when the ready queues are empty because all the processes are blocked on something. Then one possible solution is to have this now process that has lowest priority, and for our case it is a hidden priority, the user doesn't see it, and this process is always ready to run. So a basic example of a non-preemptive kernel now process implementation could be inside an infinite loop. We just keep calling release processor. I would like you to think how to change this code if the kernel is a preemptive one. So now let's go through some examples to further illustrate the idea of preemptive kernel. So assume I have P1 at low priority and it is running. And assume I only have two processes in the system, like there's no null process either. And now P2 at high priority becomes ready from a blocked state, saying it was requesting some memory got blocked, and then P1 released a memory block. That could be one situation that will cause this particular case. Then if this happens, then P2 should run, and P1 should keep its position in the low ready queue. That is, P1 gets added to the front of the low priority ready queue. So if there are multiple low priority ready processes in the queue, P1 keeps its position. It gets added to the head. And second example, let's say P1 again is lowest running, and P3 is lowest, so P3 is even lowest, and it becomes ready from a blocked state. Then what happens? Well, P1 continues to run, and P3 gets added to the back of the lowest ready queue. Why? Because P3 already got taken out from the ready queue. It was in a blocked state, but now it becomes ready. Then when it joins the queue, it should be put to the back of the ready queue. Then P1, say low priority is running, and P4 is also at low priority, and is the head of the low priority ready queue. Let's assume now P1 calls release processor. So what happens is now P1 voluntarily gives up its chance to use the CPU. Then the expected behavior is P1 becomes ready, moves to the back of the low priority ready queue, and P4 starts to run. And finally, let's assume P1 is at high priority and it's running, and it changes its priority to high again. Then P1 should continue to run. Even let's say we have a P2 that is also at high priority and it is ready. For the context switching part, we've already done most of the work for you. At least we've done context switching between two processes that do not have any priorities. And you would like to check out, study the code of this particular function. It's called process_switch. So the pseudocode is basically means we first save the current running process's context. Then we change the process's state back to ready. Then we need to update the current process to the newly selected ready process that is selected by the scheduler. Then we set the state of this newly selected process to run. And then we restore the context of the current process, because the current process for now points to the newly selected process. Then finally, by switching the stacks of the current process and the old process that gets switched out, we switch the context. Now we're ready to discuss the blocking feature of the memory allocator. So when we request a memory block and there's none, the calling process will get blocked by the kernel. What does that mean? That basically means it will be put into some sort of waiting state to wait for the memory to become available. So the kernel will put the PCB on the blocked on memory queue, and then it will set the PCB state to blocked on resource. And for our case, this resource is memory. Then the kernel will basically call the scheduler to find the next ready to run process and then perform the context switching to switch to the newly selected process. So the process that gets blocked basically gets blocked right here. It gets stuck here. Then once there's a memory available, the process will get resumed from here. When it is resumed, it will get a memory block, so a valid memory block. Then we update the memory block pointer, and then we exit from the loop because it's no longer null, and then we're done with the request memory block. To unblock a process that is blocked on memory, another process needs to release a memory block. So now let's take a look at the release memory block kernel function that is related to the blocking feature part. Well, we've already gone through these two parts in part A, so to refresh our memory, do sanity check, and then we check whether there are anybody blocked on memory. If nobody, pretty straightforward, we put the memory back to the memory pool. But if there's somebody that is waiting for the memory resource, then we need to dequeue a blocked on memory PCB. Remember, when we block a process, we put the PCB to a waiting list, and now we take it out from the waiting list. And then we have to do something to update the PCB, right? Now it becomes ready. We have to update the state and put it to the right, ready queue, things like that. Then the most important thing is we assign this memory block to the PCB. So that basically implies inside the PCB, we need to have a field to remember, yes, this memory block, we got it, and it has been assigned to the process that we just dequeued from this PCB blocked on memory list. And then we make a scheduling decision, and then we do process switch if there's a need. So the reason why we do this assignment is because of this scheduling decision may not choose the process that gets unblocked due to the memory. So we got a process that is ready because memory becomes available, and if we don't hold on to this memory and instead we just directly put it back to the pool, then it could be possible when it gets a chance to run, somebody else already steal that piece of memory. So that's why we need to have this extra field in the PCB to remember, yes, this memory has already been assigned to this ready process. So whenever the process gets a chance to run, it guarantees it will have this memory block for itself. Now I'm going to discuss the testing framework that is used in this lab. We've set up the project structure in such a way so that automated testing is possible. So during the demo, we can manually test it. We could also have an option to automatically run through a whole bunch of testing cases and as you see the results quickly. In order to do this, you cannot change any files under this source group. These are the functions written by us, and we would like to keep them as they are. And there's an AE active source group, which contains the active testing suite. So you can write more than one testing suite, and inside one testing suite, you can have more than one testing cases. But at any moment, there's only one active testing suite that can be built with other files. And this group are the testing suites written by us, and this group are the testing cases written by you. Feel free to add more source code there. In order to use the functions inside this AE group, you need to have this macro enabled during compilation. We've given you quite a lot of header files. All these header files, if they already have some existing functions defined in them, then do not change those existing function prototypes. But certain files allows you to add new functions into them. And here's the table to show you which file allows you to add new function, which file does not allow you to add new function. So for the kernel header files, these are the user level header files. For the kernel header files, like anything like k_something.h, do not change the prototypes of functions which appear in the rtx.h and rtx_ext.h files. So in these two files, there are some k_functions. So the prototype of those k_functions, they cannot be changed. Any other things, like inside the kernel, you can change them. Kernel source code, you can add new source code. You can add new functions to the existing files as well. And if you want to add new functions to existing C files, then the declaration of the function prototype needs to be added to the corresponding modifiable.h file. That basically means if you create a function, a new function in a C file, and if you want to add this function prototype to one of these header files, that's not allowed. You can only add to the .h files that are not one of these. And you have to keep existing project source group in the IDE. I've already mentioned that in the previous slides. And you may add new source group in IDE, but the existing ones, you need to keep them. And do not modify existing project file system structures. That basically means, the starter code we push to the Git repository. Don't move the folders around. Don't move the files around. You can add stuff, like add new files and new folders, and the new folders you can add files, but don't move existing files or directories around. Testing is very important. It's actually a big part of this project. So the minimum requirement is you need to write one testing suite, you need to submit one testing suite, and 3 testing cases. So these 3 testing cases, they could be 3 testing cases, each test case inside a test suite, or you can put like 2 test cases in one test suite, 1 test case in another test suite, or just the 3 of them in a single test suite. But if you really do a thorough job, you probably need, at least 3 testing suites in order to come up with some good testing cases. And under the context switching, there's a log file called uart1.log file. It captures the simulator output of UARTs. So we have this mechanism to capture the output of UART. So I would like you to submit the expected output files from your own testing suites. Say there's a create a directory called expected_output, and then put the file. The file naming convention is your group ID dash testing suite number. So this is the log file from test suite 1, test suite 2, test suite 3, so on. We also write our own test suites, and then we're going to use it in the demo. We will use the Git repository to do the project submission. I would assume everyone will be very familiar with the git command, and I have some frequently used git commands listed in the table as a reference. In our submission, we're basically using the git tag feature. So for a particular commit that you want to consider as a submission, you tag it with a symbolic name. For example, P1 will be P1-submit, P2, P2-submit, and so on. To create a tag, you first create a local tag and you give it a name. And then that's just the local tag. You need to push this local tag to the remote server so that we can see that tag. To submit the project, you first do the commit, and then you push the commit to the remote server. Let's say this is the commit you want to tag. Then you just use the git tag command to tag it with the tag name, and then some comments. Then, very important, you need to push this tag to the remote server. When you log on to the git.uwaterloo.ca, you should see this tag. And then you click it, and you can see the tag is here, and then that's the comments I made when I commit the tag, when I create the tag. You should always double check the submission was correct. During the demo, we will ask you to use this command to pull the submission from the Git repository. Here are the references I used to prepare this set of slides. So that brings us to the end of this tutorial, and also the end of the entire P1 tutorial. And I wish everyone will have a good demo. Thank you for watching.